Today we are going to be introducing limits. By the end of this video, you should be able to find the limit from a graph or by using a calculator. You should be able to describe the three situations where a limit does not exist, and you should be able to use the basic properties of limits. First, to introduce the idea of a limit, we have this situation. You have 24 feet of fencing and need to form a rectangular pen for your pet. You want the area of the pen to be as large as possible. What should the dimensions be? So since we have 24 feet of fencing, that means that the perimeter of this rectangular pen is going to be 24 feet, and we need to maximize the area. So let's start by drawing a variety of rectangles. First, we could have a pen where one of the dimensions is 1 and the other dimension is 11. In this case, the area would be 11 square feet. We could have dimensions of 2 and 10. That would give us an area of 20. We could have dimensions of 3 and 9, giving us an area of 27. We could have dimensions of 4 and 8, giving us an area of 32 square feet. We could have dimensions of 5 and 7, giving us an area of 35. We could have dimensions of 5.5 and 6.5, giving us an area of 35.75. We could have dimensions of 6 by 6, which would give us a square, and the area would be 36 square feet. If we continue increasing past 6 feet, then our dimensions will just switch, and the length and width would just switch places, but our area would remain the same as the rectangles we've already drawn. So you can see from this illustration that the square is the pen with the largest area. And as the width of our pen gets closer to 6, the area of the pen gets closer to 36. So that is the idea of a limit. And here's how we write this. We are going to use this notation. The limit, which we use the abbreviation LIM, as the width approaches 6 of the area, which I'm going to call the function A of W, area in terms of width, equals 36. So you would read this as the limit as W approaches 6 of A of W is 36. Or as the width gets closer and closer to 6 feet, the area gets closer to 36 square feet. So this is the basic idea of a limit. Here, we want to find the limit. This says the limit as x approaches 2 of 3x minus 2. So we want to see what happens as we get closer and closer to 2. So we are going to look at what happens on the left side and what happens on the right side. So I'm going to make a t-chart. So I'm going to start on the left side of 2, so with numbers less than 2. I could start with 1, maybe 1.5, 1.9. I'm going to get closer to 2, 1.99, 1.999, 1.9999, and I can just keep adding 9s, getting closer and closer to 2. And I'm going to plug these numbers in for x and see what the values are. But so I don't actually have to do the calculations myself, I'm going to use my calculator. So if I go to y equals and type 3x minus 2, I'm going to go to Table Settings, which is second window, and I'm going to change Independent to Ask. This lets me pick certain x values that I want in my table. So now if I go to the table, I can just type in my x values. 1, 1.5, 1.9, 1.99, 1.999, and 1.9999. And I can copy these down into my table. So you can see that I'm getting closer to 4. Let's see what happens on the right side. So I'm going to make another t-chart. So if I start on the right side and get closer and closer to 2, I could start with 3, then 2.5, 2.1, 2.01, 2.001, 2.0001. I'm going to go back to my calculator, type these x values in, and see what happens. And I'm going to copy these down. So again, I'm getting closer to 4. So that means that the limit as x approaches 2 of 3x minus 2 equals 4. Now, if I go back to my calculator, I'm going to change this back. If I look at what happens when I plug 2 in for x, the y value is 4. Now, it is not always true that the limit is going to be the function value, but that is sometimes the case. It is generally a good idea to go ahead and plug your x value in, because if that is the value of the limit, then that's going to be the easiest way to find that. Let's look at another example. I have the limit as x approaches 1 of x cubed minus x squared plus x minus 1 over x minus 1. If I try to just plug 1 in for x, I'm going to have a problem because I'm going to end up dividing by 0. So that is one example of where plugging the x value into the function will not give you the value of the limit. but we can use our calculators. So I'm going to type in my function. And I'm going to go to Table Settings, which again is second window. I want to start at 1, and I want to count by some decimal values. So I'm going to change this so that I'm counting by 0.001. And then I'm going to go to my table. So I went to Table Set. I started at 1 because that is what I'm interested in. And I changed the delta table, which means what we're counting by, to 0.001. So now, if I look at numbers a tiny bit smaller than 1 and a tiny bit larger than 1, and see what we're approaching from both the left side and the right side, these values are getting closer to 2, which means that our limit is going to equal 2. For now, we're going to use the calculator to help us figure out limits. Later, we will learn an algebraic way of figuring out the limits. The formal definition of a limit is if f of x becomes closer to a number L as x approaches a domain point C from both sides, then the limit is the limit as x approaches C of f of x equals L. It is important to note that the existence of a limit does not depend on f of x being defined at the domain point, like our previous example. When we plugged in 1, we ended up dividing by 0. We had an error when we looked in the calculator. So f of 1 did not exist, but the limit still existed. Let's take a look at this graph here. First, we want to figure out what is the limit as x approaches 1 of f of x. So we want to look at what's happening as we approach from the left and from the right. So this graph from the left and the right is getting closer to a y value of 2. So this limit will be equal to 2. However, f of 1 is equal to 3 because we have a closed dot at 1, 3. The limit as x approaches -4 of f of x, we want to look at when we are approaching -4 from both the left and the right, the function is getting closer to a y value of 0. And this point, f of -4, does happen to equal 0. So sometimes the value of the function and the limit are the same, but not always. Next, let's take a look at these 3 graphs. And we're going to use our calculator to help us with these. Now, I have gone back to the original settings in my calculator. If you don't know how to do that, you can just reset your calculator by doing second plus 712. And I have typed the absolute value of x divided by x into my calculator. And I want to look at this graph. I'm going to go ahead and copy this graph down onto my paper. And I know that I have open circles at 0 because if I plug in 0, I end up dividing by 0, so that is not defined. So, as x approaches 0, from the left side it is approaching -1, and from the right side it is approaching +1. So in this case, the limit does not exist. So we are going to write DNE for does not exist, because it approaches two different values from the left and the right. Next, I have the limit as x approaches 0 of 1 over x squared. So let's look at that in the calculator. So I have my function in the calculator, and if I look at the graph, this is a rational function, and I'm going to copy down this graph. I have horizontal and vertical asymptotes in this graph. So if I look as we approach 0, from the left side, the graph is going up and approaching positive infinity. And on the right side, the graph is going up and approaching positive infinity. Again, we are going to say that this limit does not exist, because if it approaches positive or negative infinity, those are not actual numbers. So since the graph is not approaching a specific number, the limit does not exist. This is the type of problem that is referenced in Mean Girls.
Limits. Why couldn't I remember anything about limits? Limits. That was the week Aaron got his haircut. Oh god, he looks so cute. Okay, focus, Katie. What was on the board behind Aaron's head? If the limit never approaches anything, the limit does not exist. The limit does not exist!
Lastly, we have the limit as x approaches 0 of sine of 1 over x. So let's look at that in the calculator. So if we graph this one, I'm curious as to what is happening as we are approaching 0. So I'm going to go ahead and zoom in. I'm going to click zoom, number 2, and enter. That's still not very clear, so I'm going to zoom in again. I'm going to zoom in one more time. So this graph is very hard to read. It basically looks like a barcode. We can't tell where these lines are, and that is because the function is oscillating as it gets closer and closer to 0. So our graph is basically a bunch of scribbles right around 0. So again, this limit does not exist because the graph oscillates. So there are 3 different scenarios where the limit does not exist. First, if f of x approaches different values from the left and the right, like the first example, then the limit does not exist. Second, if f of x increases or decreases without bound, that's just a fancy way of saying approaches positive or negative infinity, then the limit does not exist. And if f of x oscillates, then the limit does not exist. In general, when you are doing limits, a good tip is to try direct substitution first, meaning you plug c into f of x. If that doesn't work, graph it or use the table. We'll learn other methods later. Lastly, we need to look at a couple properties of limits. We're going to assume that the limit as x approaches c of f of x is L, and that the limit as x approaches c of g of x is k. If we're trying to find the limit as x approaches c of b times f of x, so some number times f of x, then that limit will just be b times whatever the limit of f of x was, which in this case is L. If we are trying to find the limit of a sum or difference, so f of x plus g of x or f of x minus g of x, then we can just add or subtract those limits, L and k. If we are trying to find the limit of a product, then that is just the product of the limits, meaning that the limit as x approaches c of f of x times g of x is just L times k. Similarly, if we are trying to find the limit of a quotient, or f of x divided by g of x, then that limit is just L divided by k, as long as k does not equal 0. Our last property is if we have the limit as x approaches c of f of x to the nth power, meaning we are raising the function to the nth power, then that limit is just L to the nth power. And we can use these when we are trying to find the limits of more complicated functions. So, we are going to let the limit as x approaches 2 of f of x equal 4, the limit as x approaches 2 of g of x equal 5, and the limit as x approaches 3 of h of x equals 6. And we're going to use these properties to find the limits here. So if we want the limit as x approaches 2 of 3 times f of x plus g of x, then we are going to have 3 times 4 plus 5, which gives us 27. If we have the limit as x approaches 2 of 2f of x over g of x cubed, then that will be 2 times 4 over 5 cubed, which is 8 over 125. If we have the limit as x approaches 2 of 1/2 f of x, then that's just 1/2 times 4, which is 2. Lastly, the limit as x approaches 2 of f of x times h of x. So that will be the limit as x approaches 2 of f of x times the limit as x approaches 2 of h of x. We know what the limit as x approaches 2 of f of x is. That is just 4. We do not know what the limit as x approaches 2 of h of x is. We only know the limit as x approaches 3. So I'm just going to leave this as the limit as x approaches 2 of h of x. And that's all we can do with that problem. It is important that you pay attention to the c value that x is approaching. because we had the limit as x approaches 2 of f of x and g of x, we can use the properties to find the limits. But because we only knew the limit as x approaches 3 of h of x, the properties are not as helpful because we cannot finish simplifying this last example.